Hello everyone, this is Professor Roman. Let's continue the field theory lectures. We have been talking about solvability by radicals. The last thing we did, let me grab that piece of paper here, is this theorem, which says that the following are equivalent for a finite Galois extension Fe. Fe is Tower abelian, Fe is Tower cyclic with prime degree steps. The Galois group of E over F is Tower abelian. The Galois group is Tower cyclic with prime degree steps. So that result gives us a connection between the field side and the group side of a Galois correspondence. But we're still missing a key piece of the picture, namely the connection on the field side between Tower cyclicness, or equivalently Tower abelianness, and solvability by radicals, or equivalently expressibility by formula. That's going to be the key connection that will give us our final result on solvability. Well, if it weren't for the issue of the presence of appropriate roots of unity lying in the base field, actually the situation would already be resolved by an earlier theorem from chapter 6. So let me repeat that here. Let Fe have degree d greater than or equal to 2, and let n be greater than or equal to 2. Then if Fe is an nth root extension, and if the nth roots of unity lie in the base field, then Fe is actually a cyclic extension, and it's a cyclic d-th root extension, in fact, where d is the degree of the extension, d divides n, and therefore since un is an f, ud will be an f as well. We don't need this part really about witnesses, excuse me, but we do need this. If ud is in f, the d-th roots of unity, where d is the degree of the extension, if they lie in the base field, then these two are equivalent. Fe is a d-th root extension, Fe is cyclic. And that is our connection between radical extensions as well as extensions that are solvable by radicals and the cyclic side, the group side. We are going to have to deal with the problem that there's no reason to assume that the roots of unity we need are in the base field. But before we do that, let's do the Tower version of this. So again, let Fe have degree 2, d greater than or equal to 2, and Tower decomposition like this. And let's say this step, the degrees here from Fk minus 1 to Fk is d sub k. If this tower is a radical tower with these step types, and if the nth roots of unity lie in the base field where n is the product of the steps, then this tower is cyclic. And the kth step is actually a dkth root of unity, that's the degree of the step. dk will divide nk for all k. This is just multitasking from the previous theorem. We're just applying it for each step. And I have this product here which tells me that, see, if the nth roots of unity lie in the base field, then the nkth roots of unity will also lie in the base field for all k. That's why I need this product. Okay. I could get away with, at least for this theorem, with the least common multiple, but later on I will want the product. So in particular, if Fe is a radical extension and these roots of unity lie in the base field, then Fe is Tower cyclic. On the other hand, if this is a tower cyclic extension and the dth roots of unity lie in F, d is the degree, then the tower is radical with these step types, these step degrees. And so Fe tower cyclic and UD in the base field implies Fe radical. So I have now my connection, or a connection, between radical extensions and tower cyclic extensions. There is one little issue probably worth emphasizing, and that is if Fe is tower cyclic, shouldn't have a hyphen there, then we know that if the dth roots of unity lie in F, the extension is also radical. But in the other direction, if we know that this is a radical extension, that doesn't quite tell us which roots of unity are required to lie in the base field in order to conclude that the extension is tower cyclic. We need an actual radical tower so we can get its step types, and that will tell us which roots of unity have to lie in the base field. So here is a sort of condensed version of this. The following are equivalent for an extension Fe of degree d. Fe is radical and has a radical tower decomposition with these step types, and this set of roots of unity lie in the base field and is the product of the step types. That's equivalent to Fe is tower cyclic and the dth roots of unity lie in F. This is about as concise, I think, as you can get it, considering that we have to make some assumptions about the roots of unity. It's as close as you're going to get to a radical extension is equivalent to a tower cyclic extension. So this is really actually quite fine as far as it goes. And the reason is this: we can take this one step further, if you'll forgive the pun. If Fe is solvable by radicals, not necessarily a radical extension, but contained in a radical extension Fr, then again, assuming the roots of unity are where they need to be, we can deduce that Fr is tower cyclic. But we had a result earlier that said that if a full extension like Fr is tower cyclic and we have an intermediate field and everything is Galois, then the lower step in particular is also tower cyclic. That was theorem 711. The converse follows easily from the corollary, again assuming that the required roots of unity are present. So that would give us the relationship between extensions that are solvable by radicals and tower cyclic. If you're thinking maybe that there's something a little funny about this, what I didn't say is that the required roots of unity here are not the roots associated with the degree of this extension, but they are associated with the degree of this extension. Okay. All right. What do we do to deal with the possible absence of the required roots of unity? Well, we need to take a look at what happens if we take a tower and lift it by some primitive nth root of unity. So the lifted tower would look like this. Well, let's gather together the results that we have demonstrated so far. First of all, in Theorem 711, we showed that the property of being a cyclic tower is preserved under lifting. So if Fe is tower abelian or tower cyclic, it doesn't matter, and we have an arbitrary extension, then the lifted extension has the same property, tower abelian or tower cyclic. Also in that theorem, and this is key here, if we have a two-tower in which both steps and the full extension are Galois, then the full extension is tower abelian if and only if the steps are tower abelian. I'm going to do what I did before and not say both tower abelian and tower cyclic. Since that's written here, I don't need to say both. On the radical side, Theorem 7.1, the property being a radical tower is preserved under lifting, and the lifted tower has the same step types as the original tower. Radical extensions have the concatenation property, and if Fr is radical, so is F normal closure of R in F. That's all from Theorem 7.1. From Corollary 2.39, way back in Chapter 2, if Fr is finite, so is this extension. Finally, Corollary 5.32, if Fe is a finite Galois extension and Fk is any extension, then the lifting has degree that divides the degree of the original extension. So we are now ready for the coup de grace. Suppose that Fe is tower cyclic and has degree d. And here is a cyclic tower. And let omega be a primitive d-th root of unity. According to statement 1 above, the lifted tower is also tower cyclic. The lifting, well, this is a cyclic tower. I don't need that. Okay. Moreover, since each step is finite and Galois, this statement, 7 here, tells us that the degree of each step here divides the degree of the corresponding step before the lifting. And so the degree of the full extension, which I'll call E, divides the degree of the original extension, D. And the reason that's important is because since E divides D, omega to the dE belongs to the base field with omega adjoined. This has to be an integer, d over E. And this is in fact a primitive eth root of unity, which means the eth roots of unity belong to the new base field, F omega. Now we can apply the corollary that we just discussed, because the appropriate roots of unity belong to the base field. We can conclude that this is a radical extension. But we need to get down to F here. But this extension is a d-th root extension. And so both steps in the tower here are radical. So by concatenation, this extension is radical, and therefore this extension, which is contained in here, is solvable by radicals. So we can now say that any tower cyclic extension, or equivalently any tower abelian extension, is solvable by radicals. As for the converse, suppose that Fe's, this Galois extension, is solvable by radicals. Then there's a radical extension Fr that contains Fe, and so it follows that this tower, Fen, where n is the normal closure of R in F, has, by statements 5 and 6, these two statements, that this extension Fn is both finite, Galois, and radical. So there's a radical tower for going from F to N with some step types. If we take the product of the step types, take a primitive root of unity of that product, and lift this by that particular omega, we get this. This is a radical tower, according to statement 3, with the same step types, N1 through Nm. Okay. We still have the problem of getting down to F. The base field, F omega, obviously contains omega. And so the corollary, now that the appropriate roots of unity are where they need to be in the base field, corollary 722 tells us that this tower is cyclic. So this extension is tower cyclic. But this extension is Galois, and it has an abelian Galois group. So it's an abelian extension. And so the concatenation property tells us that this extension is tower abelian. And since Fe and Fn are Galois, statement 2 earlier tells us that Fe is tower abelian. And we have just proved the main result on solvability by radicals. Let F be a field of characteristic 0, something we are assuming. A finite Galois extension Fe is solvable by radicals, or equivalently expressible by formula, if and only if it is tower abelian, or equivalently if and only if its Galois group is tower abelian. Now it's time to discuss this term solvable. I did give this definition some time ago for a group G is solvable, also called soluble, I think primarily in Europe, if it is tower abelian. So the term tower abelian and solvable are synonymous. An earlier corollary told us that a field extension is tower abelian if and only if its Galois group is tower abelian. So we can make the following definition. A Galois field extension is solvable if either one of these equivalent conditions hold, and therefore both of them. The extension is tower abelian, or the Galois group of the extension is tower abelian, i.e. solvable. The reason I did it this way rather than making a choice between these two is because there's a little bit of variation in the literature on the use of the terms solvable and solvable by radicals. Some authors use the term synonymously, so solvable would mean to them solvable by radicals, not tower abelian. Other authors don't even use the term solvable for field extensions, and I was tempted to do that myself. In fact, I did do that until just now, where I referred to those field extensions as tower abelian. Okay. But in any case, we can rephrase this theorem as follows. A finite Galois extension is solvable by radicals or expressible by formula if and only if it is solvable. Now let's recall a theorem from chapter 5, which tells us that the Galois group of the general polynomial of degree n is the symmetric group Sn. Also, theorem 7.9, which tells us that the symmetric group Sn is tau-abelian, i.e. solvable, if and only if n is less than or equal to 4. So, for n bigger than or equal to 5, the general polynomial of degree n is not solvable. And therefore, it's not solvable by radicals because of this theorem. In other words, it's not expressible by formula. So we now have our famous result. If n is bigger than or equal to 5, there is no general algebraic formula for the roots of the general polynomial of degree n over any field of characteristic 0. There's no quintic formula or formula of higher degree similar to the quadratic, cubic, or quartic formulas. But this corollary notwithstanding, it could still be possible that there are some integers, n bigger than or equal to 5, with the property that for every polynomial p of x of degree n, there's a specific algebraic formula for the roots that depends on the polynomial. But theorem 5.48 tells us that every symmetric group, Sn, is realizable as the Galois group of a finite extension of the rationals. Moreover, corollary way back in chapter 1 tells us that such an extension is simple. And so we could write E as Q with alpha joined. So the Galois group of QE is the Galois group of the minimal polynomial of the generator alpha. So there are irreducible rational polynomials of degree n whose Galois group is isomorphic to Sn. So we get, for any n bigger than or equal to 5, there is an irreducible polynomial of degree n over q, none of whose roots are expressible by formula. In other words, none of the roots are obtainable by any formula that just uses the 5 basic algebraic operations. I'm going to conclude the lecture series at this point, now that we have discussed the pinnacle theorem, you might say, of Galois theory, that there are no general algebraic formulas for polynomials of degree 5 or greater. But before I conclude, I did want to mention that I have added some chapters to the book, chapters that I did not cover in the lecture series. And I also moved one of the chapters that was, I think, chapter 3 and is now chapter 9 on algebraic independence. I did not cover that chapter in the lecture series. The reason I moved it is because it was a bit of a deflection from the main theme of the course, which was to reach solvability by radicals. And it kind of interrupted the flow, you might say. So after chapter 7, which we just concluded on solvability by radicals, there's a chapter on the fundamental theorem of algebra. It's very short. It is possible to prove that the complex numbers are algebraically closed, and in fact are the algebraic closure of the real numbers. using the techniques of Galois theory. Here is the chapter on algebraic independence. It's very interesting stuff, as I mentioned in the first lecture, so I would encourage you to look at it if you're interested. I then included a chapter entitled Historical Perspective. I talk about early development of the quadratic equation and the cubic equation, and the contributions of van der Monde, Lagrange, Gauss, and Galois. Also, a very brief look at Galois' life, something you could easily find on the internet. And finally, a chapter on finite fields. Finite fields are very interesting gadgets, and they have significant applications to other areas of mathematics. These chapters, these three chapters, are independent of each other, so you can read them in any order or skip any of the chapters you're not interested in. So if you are interested in this material, it is in the book, but as I say, I did not include it in the video series. So it remains only for me to thank you for watching my videos. And hopefully I will see you again in the next video course.